But I would like to see you that in some cases, physics is a part of mechanics. Okay. Yeah. So some papers. Yeah. Wave momentum. Wave momentum has a long history. You see, discussed in many papers, in books, and some points still unknown. And I try to solve. How is it to smoothly? Is it possible? Not.
With the mouse.
Hmm?
Mouse. Not with the device, with the mouse. With the mouse.
Oh. Okay. So you see remarks, much debated notion, and so on. But why I start to work in other topics, not in lattices, because two points. First is John Willis sent me his remark about my submitted paper, and in first it was very good, and then it becomes, I feel that my continuing work in lattices annoyed him. Yeah. The second point is that Michael Marder introduced his condition, admissibility condition, and my work in lattices appears like hand in hour, So, and I switch to another topic. So, what about wave momentum? In fact, it could be why there were difficulties, because wave momentum is defined as a product of two values, mass m and this particle velocity v, and each are variable. And if, for example, v is average 0, so it becomes that both variation of mass and particle velocity must be taken into account, but if they computed not precisely, so difficulties. And the point was how to present wave momentum through one variable only. So first, steady state wave. We consider from unmoving frame, the first picture, and the second moving frame. In moving frame, it is very convenient. What we have? We have the momentum at the left, at the wave, as written. It's the momentum of coordinate eta minus mass multiplied by wave speed. At the right, it is minus m0 as a rest mass. It is a mass of unmoving waveguide, initial mass, multiplied by the same speed. So, and because we have mass conservation, we come to the relation that PC, that this difference, is equal, so momentum at the, in the wave is equal to momentum in front of wave. And immediately we find solution. So momentum 6. Momentum is product of wave mass and wave speed, where wave mass is exceed of mass in the wave. So as m0 is the rest mass, m is like moving mass. So this is a solution for steady state. For non-steady state, we have such a situation usually where instead of front we have a quasi-front, like this quasi-front in line of in a chain, discrete chain, yeah. So, but quasi-front is extended, you know, relatively slowly, usually as time in power 1/3, yeah. So it allows us to ignore him based on the mass conservation, because if we have momentum in front of wave and have momentum which doesn't depend on time in the wave, so this momentum must be equal, yeah, because mass conservation has not only differential form, but finite difference too. Doesn't matter if this is flux of mass, this flux must be the same, yeah, at least in average. So we come to this we come to this formula, something.
Get rid of that. Okay.
What is this?
Yeah. Then you may be able to use the page.
Okay, okay, thanks.
Oops.
Why it is?
I'm not sure.
That's it? Okay. So we have the same expression for the momentum, but averaged over the period. If we have periodic wave. So I should mention a very good proof of the theorem on group velocity, that group velocity is equal to velocity of energy. But not only energy, any value for which conservation law is valid also should go as group velocity, yeah? Hayes presented a very nice proof. Okay. Just a moment. I will go here. Yeah. a very nice proof by variation of okay, I cannot. By variation of wave number, complex variation. You see, if wave number change to real part and I epsilon is real, so frequency becomes, you know, have imaginary addition, and exponential wave, complex wave, is represented with this envelope. This is the envelope, yeah? And again, from mass conservation is follows, and energy conservation, mass conservation is follows that these values propagate with the group velocity. So from this, for periodic wave, also could be made such a conclusion that momentum is equal to product of wave mass on the group velocity. Next point, some comments. This expression, you know, coincides with that for light and other electromagnetic waves, because from Einstein's mc squared we have momentum. Now it is wave momentum as energy divided by square root of speed, and momentum is, you know, like energy divided by speed of light, in our case speed of group velocity, the same as in mechanics, yeah? But the difference only that in mechanics wave mass could be negative 2. Okay. Yeah, you see this conclusion. Yeah, we could now use linearized solution because we have only calculate the wave mass. And the physical meaning of so-called wave momentum, mass debated, yeah? So wave momentum, it appears that it is just equal to momentum, if the average speed, average particle speed in Euler formulation is 0. Binary wave. You know, when if you take flexible wave, you consider flexible wave in the elastic beam, so we have wave mass positive, and it's clear that the left point moves to the right, yeah? But we don't apply axial force. So it appears that total momentum must be 0, but not momentum, and it appears that arise two parts of wave. The first is negative momentum, you know, the particle velocity directed to the left, and in the bending wave it's directed to the right. This binary wave first was detected in a helix. This is in the helix. If under tension, axial tension, also no no angular momentum, but because of Helix structure it must rotate. So it appears that the wave consists of two parts. One rotates in one direction, another to another direction. And okay, similar to the upper picture, yeah. So the key point is causality principle. So I consider the wave not at minus infinity to infinity, but the wave has initial, some initial time when it arises. So the wave have a front or quasi-front, where in front of it the waveguide is at rest. Next, energy partition. So shortly after my paper was published, I found that the energy partition problem was set in fact by Lord Rayleigh long ago. And he just wrote that, you see, nobody considers this problem in general. And it was, I tried to consider this in general. I list some publication, this problem was discussed. It was known more or less that in a linear system the energy, kinetic and potential energy are equal, but anyway there was no theorem that it is for any linear system. I will show that there exist cases as in a linear situation no equipartition exists. Yeah, too. So the partition depends on a different point, on different view. Yeah. So where energy are presented in general, yeah, this energy in Euler-Lagrange equation, yeah. I consider Euler-Lagrange equation multiplied by the displacement, yeah. Next step is this, and if this boundary terms B1, B2 are equal, yeah, we have equality. We have such equality. Now, so of course it could be started from Hamilton principle, but okay, doesn't matter. We have this this equality, and next is Euler theorem of homogeneous functions. So I consider the cases where kinetic and potential energy are represented, consist of homogeneous functions. Yeah. So as usual it is. If it is so, we have immediately ratio between kinetic and potential energy as the ratio of homogeneity numbers. So, and finally, equipartition exists, but kinetic energy must be multiplied by homogeneity number of kinetic energy, and so potential energy average by homogeneity number of potential energy. So in waves, okay, in waves including solitary waves, yeah. Many examples in the paper I didn't show now. So the key point is Euler theorem of homogeneous function. Orthogonality. Gilbert and Muller proved the relation 27 for two sinusoidal waves of different wave numbers. They proved for elastic layer, and I promised to Novozhilov that it's possible to present a more general situation, and it was presented later. Using only not on equations, not on constitutive data of material, not of shape of a cross section, but only on two statements. The first is Betti theorem, yeah, and the second is symmetry. That if a wave can, it is for arbitrary waveguide straight or circle, arbitrary cross section, but uniform. If Betti theorem, and if a wave exists propagating to the right, the same wave exists propagating oppositely. So, so you see this one wave with wave number k prime, and another wave is the same but with minus k prime. These two statements allow us to write Betti theorem for one wave in the second wave, and for the second wave and the third wave, where the third wave is one propagating oppositely. So, this relation, as Gilbert and Muller paper, but this vectors sigma 2 and u2 because it is two-dimensional problem, not one-dimensional. Three-dimensional, not two-dimensional. Okay, but the same formula is valid in general, but obtaining very simple without any calculations. Yeah. I see my time. Okay, have I 5 minutes? No. Okay, I finished just sorry, but I had less time. Okay. Novozhilov, find this formula for displacement of a submerged body absolutely rigid. Yeah. Considering wave equation, yeah, for water and many integrals, I found then the same formula, considering only body and the same but liquid body. So as body consists of liquid, surrounding liquid, and considering both But in general, without inspection what really is happening, what the functions. So this only conversions, and finally final displacement appears the same, but if the fluid is viscous, the final displacement coincides with the displacement of the fluid itself. But if viscosity is low, it goes first ahead if it is more light, or less is more heavy, and then slowly return back. So time dependent, and on this it shows what's the difference in acceleration and speed, liquid body and spherical rigid body of the same weight, and could be seen that they are not so far one after this both from liquid from rigid. So and then this approach of liquid body was used in some application, difficult application without complex integrals. Okay, I'm sorry.
Thank you. I do apologise for cutting you short.
Yeah.
Is there one quick burning question? If not, perhaps we could. Oh, yeah.
So when you discussed the partition of energy, do you have any example in mechanical systems where it does?
In separation energy, kinetic ether, many examples. Just a moment, I show you. It's written. It's written. Just a moment. Here, yeah. Just a moment. No. Energy partition, yeah? Energy partition, just a moment. Что? Yes, yes. Okay. Yeah.
So usually equally.
Just a moment. Examples. I mentioned the general results are illustrated by example in various types of oscillation and waves, linear and non-linear, homogeneous and forced steady state, and the transient periodic and non-periodic, parametric and resonant, regular and solitary wave. So it in all cases it was like experimental, checking this simple theory. In all cases it was okay. No contradiction was found. Yeah?
I think we'd better break for coffee, so if we could thank Professor Slepyan and